All right, so last time we were just talking about the mergers and collisions. Um, so, yeah, let's see, is this anything? I think we covered this. All right. So, and then we also noticed that if we look out there at galactic evolution, right? So this is what this is all about. And when stars that are galaxies that are so distant that their stars have had time to um, go through their entire the stars in the individual galaxies have had time to go through their life cycles, that they tend to be red. That they have an overall reddish appearance, whereas and you can measure this, right? You can measure the amount of redness on the average star, and then stars that are still evolving are more blue, and so we definitely see evidence of that. All right, so this equation, so this is how we find the distance to galaxies. This could also be called a standard candle method. And in this case, we're using Cepheid variables. The way it works is this. So we find a Cepheid within our galaxy. Okay, so that's going to we're going to call the brightness of that Cepheid B sub asterisk. Right, so that's what this little B asterisk is, and then the brightness of the Cepheid. The same Cepheid, right? So remember, with Cepheid with Cepheid variable stars, you measure the period very carefully, and then if you have another Cepheid with exactly the same period, like let's say in another distant galaxy, you find a Cepheid with the exact same period, then they both have the same intrinsic brightness. So the only reason that the Cepheid in the distant galaxy looks dimmer is because of the distance, right? And so this inverse square law. So if you take that into consideration and you solve for the distance to the galaxy, that's d sub g. So let me back up just a little bit. You have to know the distance to the Cepheid within our galaxy. So remember, the things that have an asterisk next to them, or as a subscript, is within our galaxy. So it's the brightness of the Cepheid in our galaxy, and then the distance to the Cepheid in our galaxy. Those two things are measured, and then what we do is we look at the Cepheid in a distant galaxy, and we can find the distance. And the way that we do that is really using the formula in this manner. But you actually bring the d asterisk over to the other side of the equation to solve for the distance to the Cepheid in another galaxy. All right. This is actually very much similar to homework 1 on homework problem 1 for homework 19, and we'll get into that. I'll give you an example with that one as well. All right, so I'll do a separate video for the hint, my normal hints for problem 1, and I'll include an example too, because I normally do an example with that. All right, so that's how we figured out the distance. We're using the standard candle here, or Cepheid variables. There are other types of variable stars. There are other types of standard candles that we use as well, but this is just one of the very first methods that was used. All right, so now we're going to come to something that was discovered more than 100 years ago by a guy named Hubble, Edwin Hubble, who we've already mentioned. At the beginning of this chapter, we started talking about him. But this is a discovery that Hubble made that it actually involves Cepheid variables, right? So he was the first one to look and find Cepheid variables in really our nearest large neighbor galaxy, the Andromeda galaxy. He actually found individual Cepheids. He was using a very large telescope. I might have mentioned it before, the Mount Wilson Observatory. and he measured Cepheid variables in Andromeda, and actually measured the distance to Andromeda, and it got an okay number. It's not, nowadays we have a much more accurate number, but this was over 100 years ago, and he was the first one to do it. But then something amazing occurred. Not occurred, but there were several measurements. So he measured the redshift. So remember, you look at different stars, and you'll get these spectral lines, right? So like to take these two, this broad spectral line, and then there's a narrow one, just to the right of it, and so if you sit there and you watch those spectral lines, within our galaxy, let's say, you find stars that have those two particular spectral lines, and then you go to look out to nearby galaxies. The spectral lines are shifted, and they're shifted towards the red. And then you go further out, and they're shifted even further to the red. So remember, these are stars within our galaxy. This is nearby galaxies, more distant galaxies, and even more distant galaxies. And so Hubble noticed this, this particular property of that more distant galaxies had greater redshifts. And notice, it's not just these two lines. Notice all the lines are shifted, right? Remember, all these are within our galaxy, and then you get successively further away, and that you get greater and greater redshifts. And so this is the analysis of the Doppler shift. This was called the recession velocity. And with that information, Hubble made one of the greatest discoveries of all time. Okay, this is one of the big ones. It's a wonder he never won the Nobel Prize for this. He certainly should have. But here it is. So this is what he discovered. So he looked out at these other galaxies, and he found that he got greater and greater redshifts, which meant greater and greater velocities, and he realized that meant that these stars were more and more distant. And so he came up with this formula where v is called the recession velocity, h turns out to be the slope of this line, which is now called the Hubble constant, and d is simply the distance, right? So v is the vertical axis of this graph, and then I'm sorry, yeah, v is the vertical axis, and then d is the horizontal axis, and h is the slope. All right. The modern value for h is about 72, and the units are in kilometers per second per megaparsec. So these are done in a million parsecs at a time. It's a big universe out there. So it's kind of staggering when you start to think about it. Now Hubble really started thinking about this more and more, and this was not just some coincidence that the further, go back to this picture, the further a galaxy was away from us, the more the redshift was. And he realized, he said, well, wait a second, that doesn't make sense. The universe, galaxies should be moving towards us and away from us. I mean, just kind of randomly, and there shouldn't be this overall redshift with greater and greater distance. And so Hubble thought about this, and he came to a very amazing conclusion. This is the thing that I mentioned is one of the greatest discoveries of all time. He realized that this greater velocity with greater distance was not the motion of the individual galaxies. Okay, this velocity that we were measuring, which is called the recession velocity, is not a property of individual galaxies. It's actually the expansion of space itself. All right, let me repeat that so it's kind of a strange idea. All right, so it's actually a measurement of the expansion of the universe. That's what Hubble discovered, and that's why he's extremely famous, certainly today, and all right. So really, all of our study of the universe is starts with this simple equation now. But we've got a lot more detail about this now. So here's what was going on. He realized again, the further a galaxy is, the greater the redshift. The only way that you can explain that is if the universe is increasing its size. Now, if you think about that for just a second, take a meter, the distance of 1 meter from one point to the other. You're never going to notice that the universe is expanding if you just look at a meter stick. Even if you looked at just the Earth and the solar system, you're never going to see an increase in the distance between objects because of the expansion of the universe. If you just look at our galaxy, you're never going to see that. It's only when you look at galactic distances, the distance between galaxies, that you can actually notice this gradual increase in distance. And this is what we've come to understand comes from the Big Bang, the explosion that happened at the beginning of the universe that expanded space and time outward from a single almost infinitely dense point, perhaps even infinitely dense, we don't really know, and that expansion has been happening ever since. All right, so that's what we that was Hubble's first. That was the discovery that Hubble first made, and then others have certainly measured this. This is a huge subject in the field of what's called cosmology, the study of the entire universe. All right, so again, this is only with galactic distances, and you can use other methods. There's another method for measuring distances, but they all show this kind of thing. All right, now here this is a method for finding the size of galaxies. We'll get into this a little bit later. This is not important right now, but we can measure the size of galaxies, their diameter. Now, how do we measure the mass of galaxies? Of course, we use the modified version of Kepler's third law, because you can sit there and watch a particular star in a galaxy and watch its motion. You can measure the velocity of it by using the Doppler effect and looking how the spectral lines have shifted, and you can determine what's called the orbital speed, so how fast that particular star is moving around its own galaxy, and then you can actually work out the mass and also you have to figure out how far away that star is from the center of its galaxy. If you get those pieces of information, then mass comes from the modified version of Kepler's third law. All right. Now we mentioned before that there was this dark matter that surrounds the Milky Way. It exists out there in the halo of the galaxy. It turns out that all galaxies have dark matter around them. In fact, more and more as we study this, we think that this is really the existence of dark matter might have contributed to the formation of galaxies. Why did galaxies form in certain places and not others? It might have had to do with the existence of dark matter Which again, we don't know what dark matter is. We're still trying to figure that out.